we're going to use our knowledge of partial derivatives and functions in multiple variables to be able to find maxima and minima of surfaces. So if you'll recall from single variable calculus, we have a function y equals f of x. This corresponds to some curve in the xy plane, something like this. And we could find maximum, like local max and local mins, by finding critical points. So to find local max and min, what we would do, so to find, we would find critical points. Right? And what were critical points? If you'll remember, critical points were where the derivative at that point is set equal to 0. Because critical points are points where you have a horizontal tangent line. And a horizontal tangent line is the same as a line with slope 0. So you would find the discrete set of points that have horizontal tangent lines, and then we could go through a handful of tests or methods to say, okay, well, this critical point's a maximum, or this critical point's a minimum, or neither, right? There were cases where it was neither. If you had something like y equals x cubed, this function has a critical point at 0, but it's neither a max or a min. And so this idea of defining critical points to be points where the tangent lines are horizontal, and then understanding that maxima and minima must be at critical points, then this gave us a way to calculate extrema of curves, right? But now we want to calculate extrema of surfaces. And so what will this look like? Now, when we're looking at extrema of surfaces, so let's say we have some surface doing something like this. And maybe here it's kind of extending upwards infinitely, and we could say this one's kind of extending downward infinitely. Something like this, right? Where the surface is over here. So the surface is all at the top of the screen up here. Okay, and we want to find maxima and minima here, but now we need an idea of critical points again. But now for us, critical points, we need a way of translating horizontal tangent line to the multivariable setting. Well, you notice that pictorially, if kind of without any calculus or anything involved, if I was just observing this surface and I say, okay, well, this point's a maximum or a minimum, excuse me. And what is special about this point? Well, if you take a tangent plane this time and not a tangent line, you get that this is a horizontal tangent plane instead of a tangent line. And what does a horizontal tangent plane mean? Well, the partial derivatives live in the tangent plane. So if we have some coordinate system, maybe I'll give us a coordinate system down here, like x, y, z, something like this, right? And so the partial derivative with respect to x and the partial derivative with respect to y, these both live in the tangent space here. And if it's horizontal, well, that means a line in the x direction has slope 0, and a line in the y direction has slope 0, because all lines on this tangent plane are going to have slope 0 since it's horizontal, right? And what this means that change in x and in y is equal to 0. And what this means is that we have critical points when the partial derivatives. So let's say here, let me just give a definition. Z equals f of xy has a critical point at x naught, y naught, if one of the following holds. And what we need the conditions we need for a point to be a critical point is that the partial derivative with respect to x at the point x naught, y naught, and the partial derivative with respect to y at the point x naught, y naught are both 0. This is exactly what it means to have a horizontal tangent plane. It means there's no change in x and there's no change in y. And so you can see kind of pictorially up here, like what I've drawn down here is a minimum, but we could also have kind of a maximum, like the peak of a hill, right? And here, again, it's slope 0 in any line you take in this tangent plane because it's horizontal. So, or the second condition, and this is more of kind of boilerplate. We don't really think about these kinds of critical points, but they're certainly still critical points. And we say that the point x naught, y naught is a critical point if both of the derivatives are 0, or maybe one of the partial derivatives, say f sub x or f sub y at the point is undefined. Okay, and so these are the two ways we can find critical points. We find critical points by setting the partial derivatives equal to 0 and solving for x and y values, or we're looking at the function and we can find when it's undefined. So let's see an example. Let's find critical points of f of xy equals x squared plus 2xy minus 4y squared plus 4x minus 6y plus 4. Okay, so this is some quadric surface, right? And we're looking to find the critical points. And this is a polynomial in two variables, which is defined in the entire xy plane, right? Any value of x and any value of y will spit out some defined output. So that means we don't really need to consider the second case. For this problem, like in general, you may need to consider the second case. Like if we were trying to find critical points of like this all over x cubed minus like 3x plus 1 or something like this, there are x values where this could be undefined, right? And so then you would need to consider the second one. And it's important that we remember that critical points can occur at undefined, where the function is undefined. But we notice and we kind of check that we don't need to worry about that case for this particular function. And so what we need to do is, so we need to set f sub x to f sub y to 0. Okay, so let's do that. Well, f sub x is 2x plus 2y plus 4, and the y partial derivative is that should be 2y, right? Oh, no, what am I doing? That's right. Yeah, 2x plus 2y plus 4. And this one would be 2x minus 8y minus 6. There we go. And to find critical points, you set these both equal to 0. And when we set these both equal to 0, we have a system of two equations with two unknowns. And we can solve this system for x and y values. And solutions to this system of equations gives us the critical points. And so we can use the method where we can add one equation to the other, or one expression. And so I'm going to take the bottom equation and subtract it from the top equation. And if I do that, well, I get 2x minus 2x, 0. I get 2y plus 8y, so plus 10y. And then I get 4 plus 6, which is plus 10 equals 0, right? Because on the right-hand side, 0 plus 0 is 0. And this gives me that y is -1. Well, now I know a y value. I just need to plug the y value back in to one of these equations and solve for x, right? And so you can see if I plug in y equals 1, I don't think it really matters, say to the top one here, well, then I'm going to get 2x plus, well, minus 2 plus 4 equals 0. And that will simplify to be, looks like that should also be -1, right? Because we'll have -2 plus 4, which is +2. So 2x plus 2 equals 0, which means x equals -1. And so we have one critical point, and it's the critical point -1, -1. And so this is how we find critical points in general, is we set up a system of equations given by both partial derivatives equal to 0, and then we use like linear algebra techniques or algebra techniques in general to find solutions of this system of equations. And in this case, we only had one. And here's one caution I'd like to make. Maybe I should have written caution in red. The caution I would like to make is when setting f sub x equals f sub y equals 0, always double check if 0, 0 is a critical point. Okay. Sometimes in this particular function, it wasn't the case. Sometimes when you have something like this set up, where you have a system of equations and you're solving, sometimes 0, 0 is a solution that won't be spit out. Like just by algebra techniques, it will spit out a non-zero number. And so just for caution, you always just want to double check, like just eyeball it. Just look at the functions and be like, if I plugged in 0, 0, what would happen? And here you see we'd get like 4 equals 0, which is obviously not a solution. And so in this case, we checked 0, 0 and didn't get anything. In general, the point 0, 0 can be a sneaky critical point. And it's worth expressing caution that you'll want to, again, just quickly eyeball the system of equations you've set up and say like, okay, if I plug in 0, 0, is that going to give me a critical point? All right. So what we have here is we've discussed local extrema, right? We've discussed like local max and local mins so far. So say we have some surface like this. You know, here you can see this is a minimum, but it's a local minimum because in a neighborhood, of this point, it's the smallest value, right? And so what is this local minimum? Here, a local minimum is, so let's say this is the point x naught, y naught. Well, a local minimum is f of x naught, y naught is less than or equal to f of x, y for all x, y in a neighborhood of x naught, y naught, right? And so this is a local min. It means you look at the value of the function at this point, and it should be the smallest value of the function in a nearby neighborhood. And there's an analogous definition for a local max, right? A local max would be that the value of your function is greater than or equal to the function at nearby points. For all, x, y in a neighborhood of x naught, y naught, right? And so maybe a better picture is just a sphere. Right? A sphere has very distinguished critical points of the North and South Pole. Right? And you can see here, this would be a local minimum, because if you evaluate the function at this point, it's lower than any other nearby point, right? And similarly for the maximum, here there's no values nearby that are greater than this point. And so this is the notion of local extrema, and we also have the notion of global extrema, right? Global extrema well, you can have a global max, which is, imagine a paraboloid. Here, if I can draw a paraboloid. Let's draw it the other way for a maximum. So we have a paraboloid here where it opens infinitely downward. And we look at the max here. We see it kind of the tip at the top of this paraboloid. We have a global max because there are no values over the entire domain that when you evaluate it or when you plug into the function gives a higher a larger value, right? So this is a global max if f of x naught, y naught is greater than or equal to f of x sub y. And now this is for all points x and y in the domain. So I'll just say D is the domain, right? And then there's an analogous global min. Global minimum is if f of x naught, y naught is less than or equal to f sub x, y for all, I'll use my shorthand upside down a, which means for all, right? So I could write this one as that too. For all points x and y in the domain. And so a global minimum is kind of an inverted, or an idea of a global minimum, right? Just one example for intuition here is just invert the paraboloid we were looking at. Now, let's say we have a positive paraboloid, so it opens upward like this, and you can see the the very bottom of this paraboloid will have a horizontal tangent plane. And in fact, it will be a global minimum because there are no values of the function below this point. And so it gives us a global maximum or a global minimum. And why do we care about critical points if the whole point is to find extrema, like these that we've defined here, like local max, local min, stuff like this? The whole point, so theorem, is if x naught, y naught is a local extremum, then this implies that the point x naught, y naught is a critical point. And so what we can do, this is why we narrow our attention to critical points, because critical points give us local extrema. Now notice, this says that if you have a local extremum, then this implies that the point of the local extremum is a critical point. Note, I'll note this in red here, and I'll remove all other red on the page to emphasize my point here. So, warning. This does not say the converse. The converse may not be true. X naught, Y naught, a critical point, does not imply that X naught, Y naught is a local extremum. Right, so here, this statement, this is like statement A, you could say. X naught, Y naught being a local extremum is statement A. X naught, Y naught as a critical point is statement B. What I'm saying is that A implies B, but B does not imply A. And so it's very important to notice that we may find critical points that are not local extremum. For the perfect example is what's called a saddle point. Saddle points are where you have a local max in one direction, but a local min in the other direction. So if you can imagine actually like a horse's saddle, kind of like here. So in the screen, you can see this is locally a minimum, but perpendicular to the screen, maybe the surface does something like a horse's saddle. And so maybe a neighborhood of your surface looks something like this, where again, restricting your attention to in the screen, right? So like maybe we have X, Y, Z, and our screen is the same as the XZ plane, right? And so in the XZ plane, you see we have a minimum. But in the YZ plane, we have a maximum. And this is called a saddle point. And the reason it's called a saddle point is because you can think about a horse's saddle. How does a horse's saddle behave, right? Kind of in one direction, it's increasing, right? Kind of in the same direction that the horse would be standing. And then in the other direction, it's decreasing around the sides of the horse. And so because of this, these are critical points, but they're not local extremum, because you'll notice it doesn't satisfy any criteria, right? You can start from this point, and if you go in a neighborhood, you can find, well, if you go in the X direction, you can find points larger than it. And then if you go in the Y direction, you can find points smaller than it. So it's not a max or a min, but it's still a critical point, because at this unique point, we still have a horizontal tangent plane, and it's still a critical point. And so these are points that are contenders for being extrema because they're critical points, but they may not be. So let's classify critical points now. We've defined them. We've seen how to find critical points. Now let's be able to classify them. And to classify critical points, so to classify critical points, here's what we need. We need the second derivative test. So here's the second derivative test. Let's let z be f of xy with a critical point at x naught, y naught. Then we first need a definition. Let's define the discriminant as d is the second partial derivative with respect to x twice at x naught, y naught, times the second partial derivative with respect to y twice at the critical point, and then minus the mixed partial squared at the point x naught, y naught. So you take this and you square it. This is the discriminant. And so what the second derivative test is saying is you define the discriminant and then you look at what values these are going to give you. So, and here the reason it's called the second derivative test is because the discriminant is defined by all three mixed partial, or all three partial derivatives. And remember here, f sub xy is equal to f sub yx. This is the equality of mixed partials theorem that we discussed a few videos ago. And so when calculating or classifying critical points, you will always have to compute this discriminant. You'll have to find both partial, or you'll have to find all second order partial derivatives and then evaluate them at the critical point. You plug them in, the discriminant gives you some number. And here's what the second derivative test tells you based on the number you get. So then, with this discriminant in mind, so here's the first case. If the discriminant is positive and the second partial derivative with respect to x at the critical point is also positive, then f has a local minimum at x naught, y naught. 2 is if the discriminant is positive and the second derivative with respect to x twice at the critical point is negative, then f has a local max at the critical point x naught, y naught. The third possibility for the second derivative test is if the discriminant is negative, then f has a saddle point at the critical point x naught, y naught. And if you ever compute the discriminant to be exactly 0, if d is 0, the test is inconclusive. Okay, and so to recap, here's what the second derivative test gives us. It says if you compute the discriminant, then you view whether it's positive or negative, and then you also have to view whether this piece of the discriminant is positive or negative, this piece in green here, right? You view these values at the critical point, and then you come to this chart over here, and you figure out where these calculated values land you, like in which case they land you, And then the second derivative test tells you what what kind of critical point it is. And so this gives us a nice, so the test is a little lengthy and maybe not the most fun to memorize at first, but it's very helpful in classifying critical points because instead of having to try to understand this thing geometrically, we can purely observe it analytically by looking at the second derivatives, and it tells us immediately. It's like, okay, no, this is a max, this is a min, or it's neither, or sorry, I don't know. Like if you calculate the discriminant 0, then the test is like, sorry, I don't know what's going on. So what we can do here then is there's a pretty nice paradigm for finding or classifying critical points. So this is a paradigm for classifying critical points. So step 1 is to find critical points. Find critical points of f, right? This is points x naught, y naught, such that f of x naught, y naught, f sub x at x naught, y naught, and f sub y at x naught, y naught are both 0 or undefined, right? Step 2, calculate the discriminant. So D, which is, I'll shorthand this, right? So this is, I'd rather not. So let's calculate D, which is f sub xx at x naught, y naught, times f sub yy at x naught, y naught, minus f sub xy, x naught, y naught, squared. You want to calculate this for all critical points, x naught, y naught. So if you have 5, if your function has 5 critical points, you have to calculate this discriminant 5 different times, right? Because the values of the second derivatives are going to be different at different critical points. So you'll have to calculate the discriminant however many times as you have critical points. And so step 3 is apply second derivative test to each critical point. Okay, and so here's a paradigm for classifying critical points. And we can do this. I'll go through an example of classifying critical points. I've noticed this video is a tad lengthy. So I think what I'll do is we can stop here. And then in the next video, I'll pick up right on this page. And we can review this paradigm, go through an example. And then there's a few more theorems and ideas of maxima and minima of surfaces that we can discuss before moving on to Lagrange multipliers.